All right. Welcome to reInvent and welcome to our session on what's new on Amazon Aurora. I'm Debanjan Saha. I run the relational database services in AWS, and Aurora is one of the databases that we support. Now, before I start on what's new on Aurora, how many of you have heard about Aurora? All right, quite a few of you. And how many of you are using Aurora? Okay, all right, that's good to hear and good to know. So before I get into Aurora, let me actually say a few things about relational database services in AWS. As you know that we support a number of relational databases, Aurora being one of them, and three things that we focus on, and different talks on different relational database services that you'll hear about three things: choice, value, and innovation. And let me double click a little bit on what we mean by that. If you look at RDS, we support 7 different databases, right? We support open source databases like MySQL, PostgreSQL, MariaDB. We support commercial databases like SQL Server and Oracle. And we also support Aurora, which is our own cloud-optimized database. That's what I'm going to spend most of our time on. And they all run on a managed services platform, meaning a lot of management of databases that DBs do. We make it easier for them to execute, right? So, for example, high availability, security management, disaster recovery, these are all automated in the RDS management platform, which if you are using RDS and all the databases that we support, you can use them as you go. So when you talk about value, let me explain that in terms of Aurora. This started probably about 5 years back, maybe about 6 years back now, when we first started working on Aurora. We had customers who are using commercial databases, and they like the speed and availability of commercial databases, but they're expensive, and they're complicated license management that you have to do. And we also supported open source databases, MySQL and Postgres at the time. And they are, of course, simple and cost-effective, but they are not as performing and as highly available and as scalable as commercial databases. So our customers wanted us to build a database which is optimized for cloud and which is as simple and cost-effective as open source databases, but gives the performance and availability of commercial databases. And that's what Aurora is. It's a managed service, a managed database. It has speed and availability of high-end commercial databases, but at the price point of open source databases. That's the value that we bring, and that's what we are going to get into the details of today. And by the way, we have 2 flavors of Aurora. We have a MySQL compatible version, which is fully compatible with MySQL 5.6 and 5.7. We also have a Postgres version of the database available, which is compatible with different versions of Postgres. So if you have, for example, application written to MySQL and Postgres, they can move without any change to the application. So in terms of, when you talk about innovation, Aurora is, we are innovating very, very rapidly, as you will see, in terms of new feature functions that we are coming up with. There are 3 things I want to point out in terms of where these innovations are. One is in terms of the architecture. It's a scale-out distributed architecture, which we take advantage of in doing various different feature functions, and I'm going to give some examples of that. The second thing that we do is it's also a service-oriented implementation, meaning we take advantage of a lot of web services that we have in AWS in both building the database as well as integrating those services so that people building applications on top of Aurora can build applications quickly by taking advantage of those integrations. And third thing that I already kind of talked about a little bit is it's a fully managed service. So a lot of things that people otherwise have to do is all automated in Aurora. So let's double click a little bit on each one of these. So scale out distributed architecture. If you look at the relational databases, they have been around for a long time. And really not much has changed. It's a monolithic architecture. You have different layers of the stack. You have a SQL layer, a transaction processing layer, a caching layer, a logging layer, and a storage layer. So what we did in Aurora, we have taken the logging layer and the storage layer, and created a distributed log structure storage architecture, which is purpose-built for the database. So if you look at the storage layer of Aurora, it is spread across 3 different availability zones, which are essentially data centers within the same region, in the same metro area. And we do wide sharding of that data, meaning that we slice it up into multiple pieces and then spread it across hundreds of, sometimes thousands of storage nodes. And these are the small boxes that you see there. And we make 6 copies of each data element in order to get high availability, and I'm going to get into the details of that. And by the way, the interface that we have between rest of the stack and storage layer is not traditional storage protocol like iSCSI, Fiber Channel, or NFS. It is purpose-built interface that we have built, which is essentially based on redo log. And as a result, we send very little data in terms of total volume and network packets from the engine to the storage layer. One of the reasons our performance is so much better. Now, how do we leverage AWS services? Some quick examples of that. For example, Lambda. Lambda is integrated into Aurora. You can actually issue a Lambda function from stored procedures or the triggers in Aurora. And that makes it very easy to, for example, if for every new update you want to execute a function, you can actually use a Lambda function for that. A lot of people do that. And there are a couple of other examples I'm going to provide. Now, S3, for example, we use that for backup. You don't have to schedule any backup in Aurora. We continuously back up all the time. And you can actually make use of that. And that was actually quite simple to implement. Similarly, we are integrated with IAM, Identity and Authentication Services. So various levels of database access is made easy through that integration. And all kinds of logs we upload into CloudWatch logs, so you can do various different types of processing on them. So there are many other examples. These are some quick examples of what a lot of people use in Aurora. So moving on, in terms of automated administrative tasks, all the things that you see on the right-hand side is all done by RDS platform, and Aurora, of course, is a part of that platform. So for example, automatic monitoring and high availability and failover, that is taken care of. If you want to do security management, a lot of that function, including patching and various different types of compliance and auditing, we take care of that. Various different types of advanced monitoring and maintenance function. For example, there is hardware maintenance or scaling up of your storage or your server that is also API-driven, sometimes automated, depending on what type of scale up or scale down you want. So because of that, a lot of boring things that developers and DBAs have to do, you don't have to do that anymore, so that you can focus on your business, focus on what really matters, schema design, query construction, query optimization, et cetera. So how we are doing? Now, thanks to all of you, Aurora is still the fastest growing service in the history of AWS. A lot of enterprise customers, some are shown here. These are essentially a subset of them that are public references that are using Aurora today. And if you look at why people are using Aurora, there are actually 2 types of customers or users who are using Aurora. One are people who used to use open source databases. They use Aurora because it's much faster. It's 5x faster than MySQL, 3x faster than Postgres. It has better availability and durability. And believe it or not, it's actually cheaper than what you can get through open source databases. Because it is so much faster, you can use a smaller database node, which saves you money. And I'm also going to give an example of serverless, which makes it very, very efficient and saving money even further. Migration, of course, is very easy. If you are already running on MySQL or Postgres, a couple of clicks, you can move to Aurora. If you look at commercial database users, they are moving for a slightly different set of reasons. Aurora is literally 1/10 of the cost of some of the commercial engines. You don't have any licenses to manage. It is integrated with cloud ecosystem. It's comparable in terms of performance and cost and getting better every day. And migration and tooling, although not as simple as moving from MySQL and Postgres, we provide a lot of tools and help so that people can move from commercial databases to Aurora. So let's get into various different technical aspects of what we have been doing and some of the new things we have done in the past 1 year. In order to make sure we have everyone on the same page, I'm also going to talk about some of the things we already have and some of the new things we have done, right? So that there is some context. So as I said, it's 5x faster than MySQL and 3x faster than PostgreSQL. This is, of course, based on various different benchmarks that we do. This is using Sysbench. And as you can see, we have compared with 5.6, 5.7, 8.0 of MySQL, and we have 2 versions of Aurora, which is compatible with MySQL 5.6 and 5.7. Both in terms of read and write, we do much, much better, and we continue to maintain the advantage that we have. Now, if you not only just throughput, if you look at, for example, data loading performance, this is, by the way, from Postgres, and Postgres loads data. This includes both loading the data as well as doing the vacuuming and building the index. That can be up to 2x faster. If you look at the same number for MySQL, it is 2.5x faster, right? So it becomes a lot easier to load data and then process it. One thing which is really interesting is not only the throughput, but also the consistency of throughput. This is Aurora Postgres under heavy load. And what I have shown there, the bottom graph in purple that you see, that's essentially the variability in performance that you see in Aurora Postgres as it is working under heavy load. And the one in blue on top is what you see in community Postgres. And it is, in terms of, if you look at the variance, you compare that, the standard deviation, it is 10x better or 10x more consistent than what we have in vanilla Postgres. And by the way, similar thing for MySQL. Here also, Aurora MySQL performs much better than community MySQL. Now, we, of course, have not been standing still. Besides all the software improvement we have done, we have also provided new hardware. So we started with 8XL as the largest instance, which has 16 vCPUs and 250 or 32 vCPUs and 256 cores of 56 gigabyte of memory. So that is what gave us 100,000 writes per second. We now support 16XLs, which has 64 cores and almost half a terabyte of memory. In terms of writes per second, we get 200,000 writes per second, which is about 2x improvement of what we started off with. And we are going to go to 24XL very soon. So you are going to have even more headroom in terms of the performance that you are going to see. If you look at read performance is, we started with 500K, and we are now at 700,000 reads per second. The performance growth has not been that dramatic because we are now network limited. With 24XL, we are going to have faster network, and you can expect to see much better improvement in terms of read performance, just raw throughput. Let's talk a little bit about how do we get that. I mean, of course, there are a lot of trickeries we played. The main thing that you see the difference between Postgres and Aurora Postgres and MySQL and Aurora MySQL is that we do less work and we do it more efficiently, right? By less work, I mean that we do fewer I/O. And fewer I/O means we do lower number of network transmission. We also cache prior results. We offload a lot of things from the database engine to the storage nodes. And by more efficient, we mean we do a lot of things asynchronously. We reduce latency on the path just by pure engineering. We also use a lot of lock-free data structures, which reduces the amount of contention we have in the code path. And we do a lot of things in terms of batch processing. So just a quick example of the I/O profile of Aurora versus, this is Aurora MySQL versus MySQL using EBS volume or any other storage volume for that matter. If you see on the left-hand side, there are a lot of different types of writes that are going on. There is log writes, there is bin log writes, there are data writes, double buffer writes, and also FRM files that we have to write. On the Aurora side, on the right-hand side, there is only one type of write that we do. This is because of the architecture that we have. Only thing we do, we stream redo log records from the engine to the storage node. And rest of the things are processed in the storage node itself. And because of that, although in case of Aurora, we do 6 copies, so you have to do write 6 times, as opposed to ones that we need to do on the MySQL side, we still reduce the number of writes per second for the same amount of data that we process. So if you look at left-hand side, we have, over a 30-minute period, we ran actually sysbench. Over a 30-minute period, we had 780K transactions processed by community MySQL, and we had almost roughly about 7 million I/O per million transactions, average about 7.4 I/Os per transaction. And that number on the right-hand side for Aurora, even after 6 copies that you have to do, is 0.5 I/Os per transaction, even after 6x amplification, which is 7.7x less than what we have on the MySQL side. And because of the smaller number of I/O and the network transmission that you need to do, it actually helps with the performance, the numbers I was talking about. Now, there are other things we have done. For example, this is what we have done with our lock management. If you look at vanilla MySQL, there is a big mutex, the big log that you see on the left-hand side in front of the lock manager. So every transaction that has to go and get a lock from the lock manager is getting serialized by that mutex. If you look on the right-hand side, what we do is that we have completely rewritten the lock manager as a lock-free implementation. And as a result, there are multiple transactions who can be in the lock manager at the same time, increasing the concurrency and parallelism of Aurora MySQL, which is something that leads to 5x performance improvement. Now, we talked about throughput. The things that also matter is latency. And we started working on latency a year back. So last year, we did asynchronous key-based prefetch, where we are actually prefetching in the background a lot of data based on the keys that we know we are going to access. And if you see on the right-hand side, the asynchronous key-based prefetch actually has a pretty dramatic improvement in terms of the latency numbers for a decision support benchmark. This is similar to TPC-H benchmark that we have. And if you look at the numbers, those are essentially the improvement that we have seen for various different queries, query 1 to query 22. And the biggest improvement we saw was 14.5x. And of course, something which is close to 1 is, we didn't see much improvement. And there are many where we have seen significant improvement. The other thing that we did is batch scans. So in MySQL, for example, queries are always processed, or all the fetches are done one at a time. And because of that, there are a lot of I/O that is going on, disk access and the network access that's going on. There are a lot of contention that happens. In our case, what we do is that we do batch scans inside the memory buffer. And as a result, we have another pretty big improvement in terms of what we see in terms of query latency, right? And here also we use the same decision support system. And we have seen a significant amount of improvement using batch scans. Now, what we realized, yes, those are good improvement, but we probably need to do better. And we can do actually much better, again, taking advantage of the architecture that we have. So last year, we started working on what we call parallel query processing. Now, a lot of databases claim that they do parallel query processing. What they really mean is that they are actually processing query in a multi-threaded way in the database engine itself. What we really do is that push down the query processing to the storage node. Remember I told you that we have hundreds of storage nodes behind each storage volume. Each of these storage nodes really are very powerful servers with SSDs in them. And they have thousands of cores in the storage layer. So if we could push down query processing to the storage layer, we can take advantage of this massive parallelism that we have to get really, really impressive performance improvement. And that's what we did in Aurora Parallel Query. We released that a couple of months back. And if you look at the performance number, this is really, really interesting. So, this is, again, the same decision support system benchmark that we used, the other two that I showed you. The peak speed up for some of the queries is 120x. By the way, that's 120 times, not 120%, right? And the only way you can get that is that if you parallelize in a massive scale, and that's what we have done. Now, 8 of the 22 queries in that benchmark, we get more than 10x performance improvement. And a lot of customers have been using this. This is a quote, my favorite quote from Netflix, who are using this in one of their queries, which was doing a lot of full table scans, right? So what they really did is that by using parallel query, they could reduce the scan time or the query time from 32 minutes to 3 minutes. And while doing that, because you're pushing down all the processing to the storage layer, they reduce the size of the instance where they are running that from 8x large to 2x large, which is 1/4 the size in terms of the number of cores, memory, as well as the price of that processor. So you are getting 10x performance improvement by paying 1/4 of what you are paying without parallel query. Okay? So let's kind of transition to next thing I want to talk about. Your performance only matters if your database is up. Okay, so this is one area where we spent a lot of time. Just for context, you might have seen me talking about this thing before, is that we have a 6-way distributed storage layer, meaning that every piece of data we copy 6 times, and we put 2 copies in each availability zone, right? Now, each availability zone is really a data center in a metro area. Now, we do a quorum-based read and a quorum-based write, meaning that when we write to all 6 copies, but we say that write is stable when 4 of the 6 copies are written to the SSD, right? When we read, we do 3 out of 6 quorum, although we don't really need to do that. We typically read only 1 because we know where is the latest copy. Only time we do 3 out of 6 reads that when you are recovering from a failure. We also do peer-to-peer communication in the background between storage node. For example, if a storage node dies or if it is slow, it can catch up by doing peer-to-peer replication with other storage nodes. And the volumes are striped across hundreds of storage nodes. That's for performance. Now, the advantage of doing that is that if there is a data center failure, which rarely happens but can happen, you still have full read-write availability. Nothing really shows up in terms of user experiencing any issues with that. Now, in my almost 4 years running Aurora, only once I have seen that. But still, it's a good thing to have. And that was in a typhoon, I think in Australia. We lost power in one of the data centers. And within 1 minute, all the Aurora instances in Sydney were all up and running, right? And in fact, if you didn't have a head node or the engine node in the affected availability zone, nothing happened to the database because storage layer was completely transparent to that failure. Now, what we do also that on the shared storage layer, we offer a master and up to 15 read replicas. Each of the read replicas are promotable to a master, meaning that if one of them if the master fails, we automatically switch over to one of the read replicas. By the way, you can specify in which order we should pick the read replicas, because sometimes what happens is that if you have a read replica in the same availability zone and that is still up and running, you are better off using that read replica because your application may be in the same availability zone. One new feature we have added is that we used to have a reader endpoint through which you could load balance across the read replicas. Now you can have multiple reader endpoints, and you can associate different groups of read replicas behind a reader endpoint. And the advantage of doing that, if you have, for example, different applications, and for each applications you want to associate a group of read replicas, you now have the flexibility to do that. The other interesting thing about read replicas is that we don't use logical bin-log-based replication or wall-based replication in Postgres. We use our redo log-based replication, which is a very lightweight protocol, and as a result, read replicas are only lagging behind by roughly about 10 milliseconds or so. Now, another advantage of our architecture, our log structure storage architecture, is that the crash recovery is near instantaneous. If you have used a regular database, either commercial or open source database, you know that we need to do checkpointing. Typically, checkpointing happens every minute, so every 5 minutes. And when you have a failure, you essentially have to apply all the logs since the last checkpoint in order to recover. Now, even if you checkpoint every 5 minutes, you have log for 5 minutes worth of data. Typically, log applications, especially in MySQL, for example, is single-threaded, right? So it takes much more than 5 minutes to actually apply all the logs that you have accumulated. And if that is the case, then your recovery time could be minutes, sometimes tens of minutes. In our case, the data is really stored in pages where we have all the logs associated with that page in the page itself. And all we need to do is, after a crash, we need to just reset the pointer to figure out what the last consistent point was, and you don't really need to do any other actions like application of the logs. Logs are applied on demand when that particular page is read. And due to that, our recovery time is very, very fast. Now, we are going a step beyond that. We are working on multi-master. This is something we are, by the way, doing a preview of. So if you haven't tested it out and want to try it out, you should try that. Hopefully, you should be able to make it available as production sometime very soon. The idea here is that instead of one master and multiple readers, you are going to have multiple masters. And in that case, if one of the masters fail, you still have other masters providing read-write availability, and you will have continuous availability. Now, other advantage of multi-master is that you also do write scaling. And this is one area where we actually are doing pretty interesting stuff, that if you look at the Aurora architecture, the consistency management, unlike other multi-master systems like Rack or Spanner, et cetera, there are many of them, we do an optimistic contention resolution. We assume that there is no or low contention, and we proceed that way. And if there is a contention, we recognize that there was a conflict, and we roll back one of the offending queries, right? So how do you do that? I mean, this is a quick illustration of what happens. There are different oases of consistency within Aurora. If the transactions are originating from the same head node, the head node actually can arbitrate. If the transactions are committed on the same storage node, the storage node can arbitrate. And if you have transactions which are coming from two different head nodes and involves more than one storage node, in that case, you need an external arbitrator. So in this particular case, what you have here, a blue master and a purple master, they are writing to two different tables, table 1 and table 2. They happen to be on two different pages on two different storage nodes. There is no conflict in this case. There is nothing to worry about. And it proceeds as if you have a completely sharded, completely partitioned workload. If you have a situation like this, where, for example, you have, again, the two masters, blue and purple, and you are writing to the same table, table 1, which is on page 1 on storage node 1, say, then there will be a conflict. And one of them, we do a quorum-based system, and one of them is going to win the conflict. In this particular case, the blue master wins the conflict. Okay? So as a result, the transaction T1 from blue master is successful, and transaction T2 from the purple master is rolled back. Okay? So this is also pretty simple because we are taking advantage of storage node to do the arbitration. This is a more complicated one. Here you have two transactions, T1 and T2. They are both writing to page 1 and page 2, writing to both tables. Now, transaction 1 wins on page 1, and transaction 2 wins on page 2. In this case, there is no easy way. There are two different masters involved, two different storage nodes involved, and we have a designated tiebreaker who will break the tie. In situations like this, of course, your commit latency is going to go up. And if you have a workload where this situation is very common, then performance, of course, is going to suffer. But in most cases, what we have seen, that's not a problem. Most of the multi-master workload we have seen has no or low degrees of conflict. Now, this is, by the way, from our test system. You can try it out if you are in the preview, is that there are 4 nodes in the system. As the first node, and we are running actually sysbench on this cluster. So but when you have one node up to 5 minutes, you have roughly about 12 or 15,000 write transaction per second. After that, you add at 5th minute the second node. The number of transactions you can handle kind of roughly doubles because there is limited amount of conflict. After that, you add the third one. By the way, the scaling factor here was roughly about 0.85 or 0.9, meaning that every time you add a new node, you are essentially adding 0.9 or 9.9x of the capacity of each node as if they were a single master system. And then what happens I think at the 12th minute, there was a node failure, and the performance goes down. But it recovers very quickly, because what we do is that we are constantly monitoring what happened, and then we recover that node quickly, either through a software reset, or in some cases, in this case, it was a software reset, either replacing the node, the hardware itself. Moving to another interesting feature that we recently released a couple of months back is Backtrack. Right? So you can think of this as a time machine for databases. Many times people will say, oh my God, I accidentally deleted something or did something which I'd like to undo. So this is really the undo function for databases. Very, very useful. It's much faster than the traditional ways of doing undo, which is so far has been point-in-time recovery. So it takes roughly about a minute, couple of minutes to do the backtrack, and quite popular with a lot of our customers. Let's move to the other aspect of Aurora, which people really like, is ease of use. And there are a number of features that we have worked on, which has been quite popular. One of them is performance insight, right? So, using performance insight, you can actually drill down into the performance of various different queries. You can rank, for example, the queries in terms of how much of CPU they are taking, how much of wait time they are facing, and you can actually store the data by hour, by day, by week. You can have historical data stored for 2 years so that you can go back and do the performance analysis. I believe 7 days are free. And this is something which is very, very useful in terms of monitoring your system, right? In this particular example, for example, you can set a target, what is the max CPU that you want to tolerate. You can set an alert on that so that you can get an alert when you are above that limit. If you look at that bump there, looking at the shading, you know that this is actually a CPU-bound contention that you are seeing. You can actually figure out which particular query is responsible for that. So very, very powerful tool. And we have this available for not only Aurora, but also for MySQL and Postgres and SQL Server, I believe, and Oracle is coming soon. So one tool can help you monitor performance of all the databases that you have in RDS. Now, this is one of our partners, Shalom. They integrated performance insight with APIs with Alexa so that you can talk to your database. And you can go to their booth and see a demo. I think there is a video that I have, and let me see if that works.
Alexa, open Performance Insights.
Welcome to Performance Insights. How can I help you?
How are the databases doing in Ohio?
Performance Insights reported no issues in your databases in Ohio.
Check the database performance in Northern California for the past 2 days.
On Wednesday, November 14th, the average active sessions on AMS 5.6 was 8.7, more than the allocated for vCPUs. What would you like to know about this incident?
What's causing the load?
94.4% of the load on AMS 5.6 was coming from CPU. Load from the other wave types is low.
Who was responsible for the load?
User KYLELF is causing 91.9% of the load on AMS 5.6. Would you like to notify the user?
Yes.
Would you like me to email or send the user a text message?
Email him.
Email has been sent.
Stop.
Goodbye.
All right. So, for full disclosure, I'm not using this. You might find it useful when you are driving and want to find out how your database is doing. So now moving on to other things that you do, security management is one thing that a lot of people find very, very useful, right? So we do encryption at rest. We do encryption in transit. We support VPCs, which are kind of like a firewall. And we do a lot of compliance, which people find very, very useful because that's one thing that everybody has to do in terms of keeping their data up and compliant. And a recent new thing that we have added is database activity monitoring, which is in preview, which is going to be available soon. So these are some of the compliance regimes that we support. As you can see, some of them are new. We have 3 different types of databases. We have Aurora MySQL, Aurora Postgres, and also now Aurora Serverless, and we support various different types of compliance for all of them. Moving on, this is a new thing that we are doing. So the idea here, by the way, is that there are a lot of different types of audit logs that we collect. And we put those audit logs on a Kinesis stream, and then you can send it to either CloudWatch or you can have third-party providers who can then ingest that logs and provide various different types of database activity monitoring reports, right? The partners that we are working on are McAfee, IBM Guardium, and Imperva. I think some of them might actually be here providing demos of this. You can also, for example, use Amazon CloudWatch. And once you put your data on CloudWatch, there are various different kinds of things that you can do. For example, you can search for specific events. You can monitor various different kinds of metrics using your favorite dashboard. You can do visualization. You can set alarms, etc. It's quite useful. Now, we also support various different ways of migrating data into Aurora, right? If you are using MySQL or PostgreSQL in RDS, it's actually very, very simple. We automatically ingest the snapshot and hydrate an Aurora database with that data. If you are using MySQL, Percona, Postgres, MariaDB, etc., on EC2 or on premises, there is an easy way of doing that. You can take a snapshot, put that snapshot in S3, and we can ingest that directly into Aurora. If you are using Oracle SQL Server, and recently we have added DB2, MongoDB, and Cassandra, then you can use our DMS and SCT tool. DMS stands for Data Migration Service, and SCT for Schema Conversion Tool, which are quite useful in moving that data into Aurora. These are some of the new things that we have added to our DMS and SCT. For example, we have step-by-step instruction for migration from Oracle and SQL Server. A lot of people find it very useful. In fact, this was because of various different feedback that we got from our customers. Other thing which is also quite useful is our workload qualification. So if you have a workload and you want to figure out how much work it is to move them to Aurora from Oracle and SQL Server, we provide that estimate using these tools. Schema conversion, so if you are using Oracle and SQL Server, they are not exactly same as MySQL and Postgres. We do a lot of automatic conversion of schemas, and our accuracy now has improved to 90% for both of them. And the native start point is another thing that we have added, where we can use engine native utilities, for example, PG dump and load, in order to seed your database and then use DMS to actually catch on the additional part using CDC, change data capture. Most exciting thing that we have done in terms of management is Aurora Serverless, right? This is something that we released a few months back for Aurora MySQL. The idea here is that you have applications which are intermittent in terms of their workload. They are on sometime, off sometime, or at least their workload is going up and down, right? For those kind of applications, you want to make your database follow the workload curve without an impact on the application itself. Of course, we can do that by auto-scaling, but when you auto-scale, your application gets impacted because application sessions get terminated. With serverless, we have completely eliminated that. So what we do is that you have your application that connect to a set of request router. The database instance is not really there when you do that. Now, when you send your first query, we have a warm pool of instances. We spin up an instance from the warm pool and attach it to the request router endpoint. And then we automatically scale it up and down as the workload is changing, and taking it down all the way to 0 sometime when there is no workload. And customers pay by minute, and a lot of people actually save a lot of money. In fact, one of them posted after we launched this Aurora Serverless is that I was paying some $8.30, this was on Twitter, $8.30 per day for my MySQL, and now I'm paying 38 cents for my Aurora. That was, of course, great news for customers, although my boss was a little bit worried that this might have a revenue impact. Now, if you look at how it works, so if you look at the purple line, that is actually the workload. And if you look at the blue line, this is how we are automatically scaling things up. And while we are scaling, these database sessions are still active. And as a result, the application kind of sees this really a bump on the wire. And as you notice that on the way up, we actually scale very, very quickly. On the way down, we are a little slower. Want to make sure that we are not thrashing, because sometimes there will be temporary change in workload, and you don't want to go too fast on that. So here, actually, so these are some of the new things we have done for Aurora Serverless. It's now compliant with FedRAMP, HIPAA, PCI, SOC, SOC, ISO, and HITRUST. There's a whole bunch of new regions that we have launched. So it's currently available in almost all commercial regions. Now we are just announced in the reInvent that we are now supporting the preview of Aurora Postgres Serverless. So if you are an Aurora Postgres user, go and try that out. And we also are supporting what we call a REST data API. So this was a big ask from a lot of customers. With serverless, of course, you can scale up and down very quickly, right? But people also wanted an HTTP endpoint. So if you have a Lambda app or a mobile app or an app sync or something like that, you don't have to go through a JDBC connection. You can use an HTTP endpoint in order to connect to it. So we just announced an RDS data API, which will provide an HTTP-based interface to Aurora Serverless. And that is really useful for Lambda. AppSync has already integrated with that. If you have a lot of mobile application, I think you will really find it useful. These are some of the other sessions. If you like this session, these are some of the other sessions that you might enjoy. So we have DAT204, which is a deep dive on Aurora PostgreSQL. We have DAT204, which is a deep dive on Aurora MySQL. And also there is a session on how to migrate from other databases into Aurora. So those are some of the things that you can go and check out. That's all that I had. And as you see, Aurora is ready for you. Are you ready for Aurora?